Hello, I'm Benson Margulies, the CTO of Basis Technology Corp. This talk looks at how some of our natural language processing components help applications give users a high-quality search experience. Now, we all know what search is. Well, at least we think we do. Search is this box. You type some words into it, back comes some snippets of documents. You hope that those documents are what you're looking for based on the words you typed in. Maybe you're searching the whole internet. Maybe you're searching your corporate document repository. Either way, you're often struggling to find the information you're actually looking for amidst a torrent of other stuff that happens to mention the same words. Now, traditionally, search was a sort of application way over there. It was google.com, or it was some page of some website at your company that allowed you to search the corporate document repository. But little by little, that picture has become unrealistic. Instead of search being a separate application searching a separate set of information, more and more search is the way that users expect to find what they're looking for in every application they use. And this graphic gives you a bit of a picture of this as illustrated by what Google has done. Over the years, Google has rolled out a whole series of applications. And if there's one thing all of these applications have in common, they all have search in them somewhere. Users of these applications expect to use search to find what they need.
Now, there are a number of reasons for this use of search other than just Google pushing it in people's faces. One is that we're dealing with ever-increasing amounts of data. The more data there is, the more likelihood there is that users are going to have to use full-text search to find what they're looking for, as opposed to navigating a taxonomy or a navigational structure. Little by little, other theories about how to find text in the world that involved categories or taxonomies or trees have withered away to be replaced by type at a Google box. One particular area where ever-increasing data volumes has changed the shape of applications is digital forensics. Once upon a time, the digital forensic problem, say for a cell phone, was a tiny amount of data. You could probably just page through it all and learn everything you had to. Nowadays, take down a phone, you might have 32 gigabytes of heaven knows what. And certainly forensics on computers, on disks pulled out of laptops or larger systems, has such massive amounts of data that to find what you're looking for, whether it's legal discovery or law enforcement research, you have to have some kind of search paradigm or you'll never find it. Now, another reason why search has become ubiquitous is the sad decline of spelling abilities. If nobody ever spells anything right, then it becomes much harder to find things by expecting them to match up with pre-existing categories. If you try to categorize documents by simply saying, yeah, let's keep track of all the documents that talk about Libya, you wouldn't find this tweet. Now, the spelling problem is not just humorous. The difficulty of dealing with varying spellings has very serious practical implications in the world. The Tsarnaev brothers were in part able to do what they did because no one can agree on how to spell their name, and various systems in the US government failed to match them up with information about them. Now, another driver of search is the ubiquity of small devices. In various places, a person has to select something from a list. And the longer the list becomes in comparison to the size of the screen, the less practical it is to just say, oh yeah, we'll scroll down the list of friends until we find the right one. And simple mechanisms for this, like type the first three letters, don't work very well either when you might have 200 people with the same first three letters. It's also not so easy to enter text into these small devices, and that really feeds the spelling problem we discussed before, that the text people create while working on these devices is even more full of spellos than it would be in any other reason. So now that gives you some background into why search, or how search, has become ubiquitous in application space. So let's talk about what you do about it. Now, so you might say that there's bad news and good news. The bad news is, in general, high-quality search is not a trivial matter. The good news is, however, a gigantic part of the problem of high-quality search is already solved for everyone. We've got open-source platforms that provide the basic framework for inverted full-text search engines. There's no reason for anyone to reinvent this stuff again. You can start with Lucene. You can take Lucene packaged in Solr. You can take Lucene packaged in Elasticsearch. And that saves you having to build a search engine from scratch. The bad news is that it's not so easy still to get results that people recognize. Here's an example where somebody types in the word sweet, and the next thing you know, they've got a whole bunch of search results related to suits. We'll talk later, or I'll talk later, about why this happens. Another problem really comes from semantics here. When someone walks up to a search box and types Tiger Woods, there's a real question about what they're after. It's hypothetically possible that they're looking for a large striped item sitting in nature amongst the trees. It's somewhat more likely that they're looking for a very talented golfer with very questionable morals. A straight full-text search engine can't tell the difference between those. This can have real practical implications in the world. Now, mind you, Tiger Woods might not be the first thing you expect to go shopping for on Etsy, but sure enough, you can see there is some legitimate Tiger Woods merchandise there hiding amongst a vast amount of stuff that's either about tigers or woods, or it's really quite unclear what it's doing there. Now, eventually this is about semantics. People want to type in a real query of human language and get an answer. And that's a very hard problem to solve. I'm not going to tell you that you can solve it, but I'm going to show you how that you can apply text analytics to search and get a much better approximation of this solution than what you just saw with Tiger Woods. Ultimately, one of the things people are looking for are things in the world. They want to know about a particular person or a particular place or a particular organization. What a search engine does out of the box is it searches for words, and those are just not the same thing. Our products at Basis Technology help customers build search applications that give users more relevant results. Where relevancy ultimately means are the documents or results you pull up really related to the things in the world that the user is trying to search for. So that starts with, if you just think of it as a search on words, are we at least finding people words they recognize as being relevant to the problem at hand? Can we help people search for the names of real-world items? Can we find places where documents are mentioning particular things in the world? And that's enabled by our ability to say, this document has a string which seems like it might be talking about someone in the world, but is it? Now, to understand how we help with this, it's useful to have a picture in your mind of what's really going on in an inverted text search engine like Lucene. So here's a little example derived from German. And we'll look at what happens in really what you can get by just simply deploying the open source components available for German. We start with a document containing what Mark Twain would call an awful German compound. And what happens is that we take that word and we put it in lowercase and we run it through what's called a stemming algorithm. What that is will become a little clearer in a moment. And we put that in the index. In this case, what ended up in the index is exactly the same thing we started with, except with all the uppercase taken out. Now, that thing is a compound. It's really built of two separate German nouns. If the user searches for the second one of those nouns, what happens? Well, we take what the user typed in and we lowercase it and we stem it. And once again, the stemming is not very interesting. So we just get that second word and we go looking for it and we don't find it and we are sad. Now, here's another example from a slide I showed you before. In this case, the document contained the English word suit. That goes into our index in a very simple way as itself. And then the user searches for suite, looking for hotel rooms, I suppose. Now, the stemming process converts suite to suit because the stemming process is just a simple pattern match that in this particular case will strip final e's off. And now all of a sudden, we've got a hit that we didn't want to have. We went looking for suite and we found suit when we should have found nothing, or at least actual documents containing suites. Now, if we add more significant text analytic processing, things get better. In this case, we take our German word and we lowercase it, and instead of just trying to stem it, we actually split it into its component bits and pieces. You'll notice that that's not just splitting the word into two pieces. If you look at the first of the two pieces of that compound, it has lost the letter N off the end because that's what the noun really looks like if a user was going to search for it. So now the index has both of these terms. In fact, the index also has the full compound in case someone wants to look for it, but the slide was getting crowded. So as a result of this, when the user searches again for the second word of the compound, they get a match. They are happier. Or in our other example, the same thing is happening. In this case, the same thing happens on the left because suit really doesn't undergo any interesting transformations. But when we put suite into the process, we take the lemma of suite, and guess what? The lemma of suite is not suit because suites and suits have nothing to do with each other except that you might hang one up in the closet of the other. And so now suite fails to match suit. We don't get that result, and again, we're doing better. Here are some more examples of where all this stuff comes from, which is cases where languages can show you something superficial that appears to be related that isn't. So here we have some French examples involving the collision of the word for summer and a form of the word to be, or the word or the verb to drink and the word for some woods. Here's some similar examples for Spanish. Here's a few more examples of how German builds compounds and shows you how different the compound nouns are from the individual pieces of them that make them up. A whole other problem, however, comes up once we start to look at Chinese and Japanese and Korean and Thai. In these languages, if you look at it, you will see a sort of a suspicious absence of white space. Now, they invented paper in Asia, and so they hate to waste it on something as useless as white space. Instead, the human brain turns out to be really good once you learn the language at figuring out where the words are, but computers are really stupid about this. And so before we can build an index based on words, we need some words. A text analytic process can find the words by a combination of dictionaries and statistical models. Now, all this adds up to a suite of tools we call the Rosette-based linguistics. This includes tokenization, which was where I just was, which is splitting a string of Asian language text into its words. The lemma process, which is to map words to their base dictionary form to get better precision when we look for them in a search engine. Decompounding, splitting compound nouns up, and then part of speech tagging and noun phrase extraction and sentence detection, which are not really that directly applicable to search engines, but are sometimes built into higher level text analytic components that are. Now, the next thing that I mentioned in passing was our ability to look in a document and say, where are the strings in this document that have every appearance of being mentions of things, otherwise known as named entity extraction or name tagging? I'm not going to talk about that in any detail because in very close to this video, you'll find another video in which one of my colleagues presents a lengthy explanation of our ability to do named entity extraction. However, once you have names, you have to deal with the fact that names are a particular target for variation and spelling problems of one sort or another. If somebody's name is Jesus Alfonso Lopez Diaz, there are many different ways somebody might spell that person and really be referring to the same guy. Here's a few of them. And if you really want to help people find things based on names, particularly names of people, it's just not good enough to go looking in a search engine for some sort of phrase query. If you look, say, at the next to last one there, you'll see a reference to a common nickname in Spanish for Jesus, which is Chuy. You're never going to match Jesus and Chuy by running a simple full-text search engine or even producing a lemma. This requires special purpose code that knows particularly about phenomena in names. Name problems also come up in a cross-language context. Here are a lot of different ways that people can refer to the President of the United States from the historical past, Franklin Delano Roosevelt, and all of these are real references to the same guy, and the Rosette Name Indexer can give you a score that relates each one of these forms to the normalized form of his name. Even once we can find the strings in documents that refer to things, entity mentions, named entities if you like, that still hasn't told us who these people are. The most obvious example of the problem at hand is our matching President Bush in recent United States history. You can find references to George Bush in documents, or President Bush, and that does not tell you, just by seeing President Bush, which President Bush it is. You really want to know which President Bush it is in many important applications. And to do this, we have to use document context and other more complex models to perform a test called named entity resolution, or entity resolution, which maps these string references to the actual things in the world. Here's a picture of a sort of search application you can build using this. And the important thing about this picture is the left-hand side, which shows you facets. Now, faceted search is something we've all seen a lot. It's most frequently used for structured data like price ranges or categories. But if you've got a whole lot of text to find your way around in, you don't have that pre-existing structure. What you want to do is infer structure by looking at the documents, and the first thing you can do to infer structure by looking at documents is find the names. But if you have 6 different names that refer to the same person, all those Alfonso Diaz people or a couple of different references to President Bush, your facets don't really work right. You have too many of them. They're very noisy. The effect of doing entity resolution is to first and foremost give you nice clean facets where you only have one navigational facet for the thing in the real world, and that allows you to much more rapidly home in on what you're looking for. The same set of stuff also applies in the forensic domain, as I mentioned quite a while ago in this talk. And so here's a snapshot of Autopsy, an open source digital forensics platform that Basis Technology helps to maintain. In Autopsy, we've integrated full text search and entity extraction so that you can much more rapidly locate information in a large forensic context, like one large disk drive or even an entire farm of disk drives that you've collected somehow or another, and find the relevant information on the captured disk drive much more quickly than if all you could do was go searching for exact keywords. We've just had a look at the reasons why search has become ubiquitous in applications, at some of the things that are barriers to high-quality search, and some of the opportunities for using text analytics to give users a satisfying search experience in applications. In particular, I've tried to show you how some of Basis Technology's products can be integrated into your search application in order to give your users a high-quality experience across a wide range of languages. These components come with a simple integration into Lucene, Solr, and Elasticsearch, and we can help you integrate them into virtually anything else in creation. In general, we look forward to working with our customers to help them solve real-world problems, and we hope to hear from you sometime. Thanks very much.